So a question that came up tonight during my Calc 2 class was find the area contained inside of both r equals 2 times the sine of theta as well as r equals the sine of theta plus the cosine of theta. Now, first good idea would be draw both of these graphs. R equals 2 sine of theta will be a circle passing through the pole, extreme point in the y direction. R equals sine of theta plus cosine of theta goes through the origin like so, comes back around kind of like this. So the region in question, what's inside both of these circles, is going to be this little region right here. So what I'm going to do is try to expand this region a bit and see if I can draw it in a believable fashion. So we had this, and then we have kind of a sharp point here where we transfer over to the other function. Now, we see a point of intersection between these two curves here. Now, this curve down here was r equals 2 times the sine of theta, and this curve up here is your r equals the sine of theta plus the cosine of theta. Now, what this means for us is that through the first part of the region here, as theta starts to increase slowly, the only thing that is acting as a boundary for this region is r equals 2 times the sine of theta. So the total area is going to be area bounded by r equals 2 sine of theta until the point of intersection, or angle of intersection, plus all of the area that we see in this region here. So that area is being bounded by r equals sine of theta plus cosine of theta. Area bounded by r equals sine of theta plus cosine of theta from point of intersection to where curve hits pole. Now, both of these two curves hit the pole at two different angles. First one is very straightforward. This will be at theta is equal to 0. Then as we start rotating through the first quadrant, there will be a point of intersection here. Then as we start rotating through the rest of the first quadrant as well as the second quadrant, there will be an angle where this thing hits the pole. So first, the point of intersection of the two curves. We get a point of intersection by setting these two curves equal to each other. So 2 sine of theta is equal to sine of theta plus cosine of theta. Subtracting the sine of theta from both sides, we get sine of theta is equal to cosine of theta. And there are two places on the unit circle where that happens. Only one of them is in quadrant 1. So the angle of intersection for these two curves is going to be theta is equal to pi over 4. Next, we'll need to figure out where the curve sine of theta plus cosine of theta hits the pole and what that angle is in quadrant 2. So sine of theta plus cosine of theta is going to hit the pole when r is equal to 0. This lets me know that the sine of theta is equal to the negative cosine of theta. Now, there are only two angles where that occurs on the unit circle. There's only one of them in quadrant 2. And that is going to be where theta is equal to 3 pi over 4. So based off of the description that we gave earlier, the total area is going to be 1/2 the definite integral from starting angle to ending angle of the boundary function, or rather, we already had the 1/2. So 2 times the sine of theta, quantity squared, d theta, plus the angle, pi over 4, to the angle where it hits the pole again. So from pi over 4 to 3 pi over 4 of the sine of theta plus the cosine of theta, quantity squared, d theta. And integrating this will involve a power reducing identity. This will require you to FOIL and then use a U substitution. Hopefully the setup is enough. Final answer for this one, I believe, is in the back of the book. So, try it from there.